Thank you very much. Yeah, you see the title, Cyborg Experiments, and that's what it is. Going to be talking about a set of experiments, so it's all very practical. So if you come wanting to listen to some mathematics, you're in the wrong place. There's obviously a lot of that underlying it, but mainly it's looking at a bunch of experiments. Cyborg is a cybernetic organism which is part human, part machine, or part biology, part technology. So it's looking at that merger. I think the important thing to think about is that it's not sort of two separate... Oh, this is going on and off. It's whether I'll use... Have we got a hand mic I'll use instead? This is looking a bit... Okay, there we go. Hopefully that's better. Can everybody hear me now? Wave at the back if you can hear. Thanks very much. Hey, there we go. That was without implants. It's fantastic. Okay, when we're looking at cybernetics and cyborgs, you're looking at the whole system, really. So it's not looking at putting a human and technology together and seeing what the two things can do. You're looking at seeing what the whole system can do as a cyborg, essentially. So just to start us off, I'm going to take us way back in time into the last millennium, those of you that remember, just to say where I've come from. It's now more, this term biohacking is now become a more popular term to say. Might even be some biohackers here in the audience. But in the mid-1990s, there were various science gurus, people like Ray Kurzweil, that were saying in the future we won't need car keys, we won't need passports, we won't need credit cards. What we will have is a little implant under the skin that identifies us to the system around us. But nobody had tried it until I did. This is a young version of me when I had dark hair. This is what academic life does to you. Worry about your wife and all that sort of thing. And this is my doctor. And what he's doing is implanting in my left arm this device. The thing on the right hand side, not the thing on the left hand side. And what this is a radio frequency identification device, RFID. This was back in 1998. Now at the time when this was implanted, it was a little bit different. Nobody had actually tried it before. And what we got it to do, we linked it to the computer in my building in Reading in England. And essentially in the doorways, each of the door frames, we have a big coil of wire with an electric current passing through it. And if you have an implant like that, it doesn't have its own power supply. It picks up power inductively. So you have current in the coils in the door frames. And when you walk through, current is induced in the coil, just like a transformer. It operates the same way. Is induced in the coil. That power is used to transmit a code which is stored in the chips in the bottom half of the implant. It transmits that code back to the coils in the door frame, which are linked to the computer, so the computer knows essentially when it's you and where you are at particular points. So what we got it to do, as I walked around my building, walked down the corridor, the computer knew it was me, so the lights came on. Walked towards my laboratory and the door opened automatically. I mean, it was really cool. Fantastic stuff. And then coming through the front door, the computer knows me. Hello, Professor Warwick. Hey, quite formal computer. Now it says hello, Kevin, so we're all right. But I got a lot of criticism at the time. What do you want to do that for? Nobody's ever going to want to use anything like this. We'll have to say now, I don't know, first of all, does anybody have a cat or a dog with a chip implanted? Please. Thank you. There's some hands going up. You can feel happy that your animal is safe because this technology was fully tested on humans before your animal received it. But the biggest use, I think, there's all sorts of use now in the United States, and particularly under the Obama healthcare plan, but even then before that, but now particularly under Obama, people who have diabetes is one area, or epilepsy, now have chips of this type implanted so that when it's serious stuff, when they go into hospital, the hospital authorities know what medication to give them. So literally by scanning the chip, they know this person, and if you can reprogram it so they know what medication you were given last time and if there was any bad problems with it and so on, so that it can be updated. So it's like having a bit of a health record that you carry around in your body. And it's just one example. But the key thing is to think on this. When you have technology like that inside you, effectively you and the external technology, in this case it was the building, in my case, you become one system. So it was myself and the building were one cybernetic entity, and the building was doing things for me. I guess I could have also done things for the building. But let's have a look at experiments number 2. And this is the sort of thing, often I get students coming to me and saying, hey, I would like an implant, what sort of thing can I have? Well, stay tuned. This is the sort of things you can do, because this is what my students now are actually doing. And I've called it sensory substitution, which we will see what I mean by that. And here we go. This is Jawesh's left hand. What he's having are magnets implanted in his fingers. So Jawesh has got 2 magnets implanted. I've now got 3 students that have magnets implanted in this way. Now, one thing to note, that all of the projects that I'm involved with, we have to get ethical approval. It's always a bit difficult, particularly from the university. The university has these committees and they have to say, yes, ethically you're okay. And in this case, which we have to get ethical approval from the committees, it's a bit of a problem, because if you look at the guy that's actually putting the magnets implanted, you'll see he's got tattoos on his arm. If you look closely, look down here, you'll see he's got some tattoos. That's because he is a tattoo artist. He's not a doctor in that sense, not a medical doctor anyway. But the problem is, although he's a tattoo artist, he calls himself Dr. Evil. That's the name he uses. If you go and you'll find his website, Dr. Evil, and he does these implants and so on. Now, on the forms we have to fill in for the university, it says, there is a line that says, who is carrying out the medical procedure? And we have to put Dr. Evil and then the university authority. So they give us all sorts of problems with that. There's an X-ray. You can see the magnets implanted in Jawesh's fingers. And now we'll see what we're doing with them. On the baseball cap, he's got ultrasonic sensors. Ultrasonic sensors give a pretty accurate indication of distance to objects. The output from the ultrasonic sensors is fed down into a coil of wire, which is round his finger. You see the coil that's around the finger. So what happens, as an object comes closer, or if he moves closer to an object, because the object's getting closer, the ultrasonic signals change. The output from the ultrasonic sensor provides more of a current to the coil, which vibrates the magnet more or less, dependent on how close objects are. So the closer the objects come, the more current in the coil, the more the magnet vibrates. The magnet is implanted in the finger. The object's further away, the magnet vibrates less. So essentially the student can feel how far away objects are, if you see what I mean. Now immediately there is a use, an application for people who are blind. Not to repair the blindness in any way, but they can feel distance to objects. So that's what's going on there. Now Ian Harrison, who's a PhD student with me at the moment, he also has the magnets implanted, and what he has done is link it up to an infrared sensor. So in this, infrared is like a heat sensor. So he can detect hot objects from a distance. So literally he would be able to scan round and say, you are hotter than you are, in a temperature sense, not in a, I mean that's something else we can work on, the other sense, but temperature sense. And now of course this has immediate application in the military domain. Because if you can imagine now you are a soldier and you're about to go into a room and you have no idea whether there's anybody in the room, then with this implant you can just put your finger around the corner of the door and just scan around the room. Hey, there's somebody over there and somebody over there. So you'd know pretty accurately where the people are, and you'd know how hot they were as well. I don't know whether that's a good point, but you can detect people even around or potentially through walls if you can detect them that well. So there's potential use for it, but there more than likely will be other uses which we don't know. There are a lot of companies at the moment involved with technology, particularly mobile technology, where the amount of information that's coming through is too great to feed in to the human. The interfaces are simply not possible. And looking at other ways of feeding the information into the human brain is a big technology movement, particularly in the military domain. Getting information into the human brain as quickly as possible in quite a rich form is an important area. And that moves us on. This is another student, Ashley, and he's looking at some work a guy called Paul Bakirita did a while back. What Ashley's done, he has a little array of electrodes, and this array you put on your tongue, and essentially you can send a whole bunch of signals, very small electrical pulses, into the tongue to communicate with the brain in that route. Now, it turns out, first of all, that even if you've never done this before, you put this on your tongue, and very quickly you can recognize letters, shapes, all sorts of things, without, it's almost zero training. So it's something very quick that you've got, that you can recognize words and messages. Particularly what's very quick is directions. If you're given directions by different pulses as to which way you should turn or go, you can receive the sort of the commands in this route. Now it also turns out that it is a very, very rapid route from the tongue to the brain. It's not something we tend to use at all. We use our eyes and our ears. We don't tend to use this route other than for babies. I don't know if any of you have got, I see one or two older people here. If any of you have a baby, the baby very often, first of all, is putting things to their mouth to learn different shapes and things. And we don't, why are they doing that? Well, there is a very rapid route from the tongue, the sensory mechanism on the tongue, straight up to the brain, and we know at the moment very little about that particular route into the brain. We know quite a bit about the optic nerve, we know probably even more about the auditory nerves, but going from the tongue into the brain, we know very little, and yet using it as a route, an alternative route, rapid communication to the brain is quite an exciting possibility. Okay, not necessarily with this enormous set of array electrodes like that. That might not be the ultimate route. It might be just a little thing that you put on your tongue, but it could be a potential alternative route to interacting with technology. but we can learn a lot from it. Now, for something a little bit different, when you think of a robot, you might well think of something that is controlled by a human, the sort of the wheelbarrow robot for bomb disposal, or you might think more of a sci-fi type of robot. Well, now we have to think as well about robots that have their own biological brains that maybe are not too dissimilar to you or I. And I'm going to describe what I mean by that in a second. First of all, though, I want to introduce you to some of the robots I get to interact with on a daily basis. First of all, you're going to see Morgui. Morgui is a robot head with 5 senses. Morgui is I'm sure you know, is Mandarin Chinese for magic ghost. It's supposed to be a sort of scary robot. But anyway, it has 5 senses. And then we'll see some little mobile robots. It's more the little robots that are of interest for this presentation. I've taken this from a BBC programme called Inventions That Change the World.
One of the AI community's leading lights is Professor Kevin Warwick.
Well, this is a robot head.
Dissatisfied with vacuum cleaners and robot dogs, Kevin's gone one stage further. His cyborg comes complete with
radar in its nose and an infrared top lip.
Is it intelligent?
Well, in a very limited way, I guess it is. It's sort of a basic instinct. What do I do with this information that I'm getting? How do I move? How do I operate if this signal is different?
So what's it doing now?
Well, if you clap your hands...
Oi, over here. Oh, it did it.
It's making basic decisions. All we've got it doing here is programmed to make basic decisions based on that sensory information that's coming in.
Getting the information in is nothing. That's like picking up a book. That's not an intelligent thing to do. Reading the book and knowing what the words mean, that's surely the intelligence.
Many machines can read books nowadays, but it means something different electronically to the machine as it would mean to a human.
Though the cyborg head does a reasonable job of sensing, it can't really interact with or explore its surroundings. It's fastened to its robot arm. And according to Kevin, it's only as intelligent as a dishwasher. If that's a dishwasher...
Yes.
Where are these in terms of... Are they dolphins, chimps?
I think you'd have to say it's about the 50 to 100 brain cell area. So realistically, you're talking slugs and snails.
But a slug and a snail, they know to eat. They know. These things don't...
They have some innate abilities.
There's no self-preservation with that.
Well, we do have. The power supply, they don't have their own batteries. They each have power they're picking up from the floor here. That's where they're getting their energy. That's where they're getting their food
But
from.
if you turned off this section of the floor,
if we turn off this section, they have a basic instinct to go and look for some power somewhere else. They will keep going to do that until they find some.
So if I put him down,
it should go off looking.
So he'll have to go and look for power. And are you going to tell him to do that?
No, it's an innate response for that robot. It's a basic thing of its life. Yeah.
No, his lights have come back on.
Lights have come on.
So he's found power.
He's happy now that it's getting power. Away to go.
But these then are as intelligent as slugs.
It's different. But in terms of numbers of brain cells and that sort of thing, yeah, we have slugs. Probably you could say we're up to bees and wasps, the sort of tens of thousands of brain cells, is about as good as you can get. Yeah.
Bees and wasps.
Yeah.
Right.
Don't know if you recognise the guy. I have to say, I know none of you ever use Wikipedia, but if you did, the original quote from this, the original quote is on Wikipedia, or WikiQuote, which is that our robots have 50 to 100 brain cells, which makes them about as intelligent as a slug or a snail or a Manchester United supporter. See, we've not got any. I told that in Scotland of all places, and the room was full of Manchester United supporters, and it was not a good idea. So I see I'm at home here. That's all Barcelona fans or something here. But it's those little robots that we're looking at there. In the pictures we saw, the robots have microprocessors, computers for brains, and we can look at how they learn, how to move around, how they can communicate with each other and teach others, that sort of thing. So we can look at artificial intelligence per se. But what we've done more recently is replace the computer brains of the robots with biological brains. So literally give them a brain of the form that we have. This, whether you can see, the words don't matter so much. The right-hand side shows that the physical body of the robots that we have is what you were looking at, is with wheels, just a small device, ultrasonic sensors, so it has sensory input, it has a way of moving around. That's the physical robot, the external, the body. On the left-hand side, it says MEA. What that stands for is multi-electrode array. It is actually a little dish with electrodes on the bottom of the dish. What we do is take brain cells, neurons, from rat embryos, separate the neurons using enzymes, and then place them in this dish, and then grow them. We have to feed them with minerals and nutrients. In fact, it's a little pink liquid. It's very much like some of the energy drinks. If any of you are athletes, you have these energy drinks. It's very much like energy drinks, except that it's not got so much sugar in it. And the second thing is it costs a lot more for some reason because it comes in this special laboratory bottle. But we feed it, the culture which is growing, these are brain cells. It's really interesting, when you lay them down, you've separated these neurons, these are biological neurons, you can look at them under the microscope, and within something like 20 minutes, the neurons are putting out what look like little tentacles. Because neurons have that, they want to communicate, they want to link up. And when these tentacles from one neuron links with another neuron, they start sending signals, one way or the other. And as the different connections are made, so you start to get a brain forming. And it's very non-linear. In some parts of the dish, on the array, you have lots of neurons. In some parts you have very few. Some have long connections, some don't. After about 10 days, we have a little brain there with something like 100,000 to 150,000 brain cells. That's in this two-dimensional array. What this multi-electrode array looks like, here's another picture of it here. The gold terminals around the outside, that's what we can use to push signals into the brain. The brain is actually growing. We see the black rings there. The black rings we need to try and make sure that it doesn't lose moisture. It has to be kept moist, and they help to keep it moist. We don't want it dehydrating at all. So after about 12 days, we can then send signals into the brain. The brain is in an incubator, kept at 37 degrees centigrade. We have to keep it at appropriate temperature. We send signals into the brain, zing, 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 they'll go through the brain, and we pick up the signals elsewhere on other electrodes, and we connect that to the robot body. So we give the brain a body, and hence the loop is the ultrasonic signals from the robot. When the robot gets close to a wall, those signals stimulate the brain will then have a think. We get an output from the brain which will change the direction of the robot, and then off it goes until it gets a stimulating pulse. But as you'll see now, you're going to see the robot with a biological brain moving around, and first of all we're going to look at it after about 10 days. This is after the brain has developed for about 10 days. You'll see how it performs. So what we want it to do is it'll start moving in a second, and what we want it to do is move towards the wall, detect the wall and turn right. That's all we want the brain to do. Fairly simple task. There we go. That's what we want it to do. But then we'll see here, it sort of changes its mind and turns round and crashes into the wall and so on, which is not what we want it to do. But this is a baby robot. The brain is only 10 days old, give it a chance. And again it changes its mind. And it moved towards the wall. Great, that's what we want it to do, lovely. Detected the wall, and that's not what we wanted to do. We don't want to do that. But you can see how it's going. Occasionally it gets it right, and sometimes it gets it wrong, and then it changes its mind. Oh, it's got a mind of its own. Well, it has got a mind of its own. That's exactly the point. It's making up its mind. It's a biological brain. Now, what we can look at under the microscope is the development of the brain. And what we can see, because this brain is in its body for about 1 hour every day. And we can see how the brain develops day by day by day. And what we can see is a process called Hebbian learning, habitual learning. This is something Donald Hebb looked at, wrote papers on in 1947, 48, something like that. And it's simply the fact that if some neurons fire, they will stimulate other neurons to fire, and every time that happens, the pathway between those neurons strengthens. It's simply habit. And in humans, you witness it in various ways. Habits form. Okay, we have bad habits like smoking. You do the thing, every time you do the thing, so the pathways, so it becomes very, very difficult to break the habit. It's not because there's something in mid-air. It means you have neural pathways that are very strong, that you've got to try and overcome them. I mean, one way of kicking the habit of smoking would be if you allowed a surgeon to go in and cut the pathways. Then you could that you might think that's a drastic way of doing it, but it kick you. Another way is you've got to try and pick up habits that overcome those habits, which could be more difficult. So we can look at how this learns. Now we're going to move ahead in time. Going to skip ahead. Here is the same robot. Ding, there we go. Same robot after 2 months. And the brain has now developed. It's the same robot, the same brain, but we've moved on to 2 months. And now you'll see how it is, how it's performing. And we've been able to witness the changes in the brain over that period, which is important. So off it goes, detects the wall, turns, doesn't seem to change direction, detects the wall, turns, and it's a little bit boring now, because it's just doing, this is what we wanted to do, this is what it's developed, it's had all this habitual learning, it's learned right, detect the wall, turn right, the wall, turn right, off it goes. And I mean, in a way, this, of course, I've chosen a good example. We have other robots which, they're still awkward robots, and they still play up, and they're not as perfect. This one has been a perfect student. And you have to remember this. This robot has been learning in a laboratory in the university. So this robot has had a university education. It's not a stupid robot. I can't tell that because now we're charging fees for students, so I can't tell that to our Vice Chancellor, otherwise they'll start charging the robot fees for being a student. What we are doing now, but you can see how it's improved in terms of its learning capabilities over that period. What we are trying to do, the big question, is to put the robot in different positions and see how the memories of those positions actually manifest themselves in the brain, in the culture. What is a memory? We don't really know. Is it diffuse in the brain? Does it appear in particular regions of the brain? Well, we've got a little model brain here that we can look at and see what's going on and actually try and investigate that. And what we want to do, even if we don't fully understand what a memory is, what we want to do is apply new neurons as time goes by and apply stem cells to try and keep those memories. If we can get this brain, as some of the neurons start dying off, we can get the brain to keep the memory of what it's supposed to do and what it's about, then maybe, just maybe, in years to come, we can apply some of the same techniques to help people who are suffering from Alzheimer's disease and dementia. So it's a big arm waving, but we've got a long-term goal there, and we can look at some of the basic physical things that are going on in the brain with our little model brain here. The two other things to say, we are also now culturing, growing in 3 dimensions. So this is using a latticed structure rather than a flat 2-dimensional array. The big thing that does is take us from something like 100,000 brain cells to about 30 million brain cells, simply by going up the extra dimension. So it's looking at now 30 million neurons in a robot body. The other thing to say, we have human neurons that we're using, not just rat neurons. Well, I need to qualify that. We actually buy them from an American company. So they are, technically they are American neurons, but it's as close as we can get to human neurons. Right, now for something a bit different, a different type of cyborg. There's all sorts of questions whether cyborgs are just to do with enhancement, which we'll have a look at in a moment, or therapy. Therapy if you're helping somebody who has a problem. Well, what I'm going to describe first of all is more the therapeutic side of things, and some of you may well know about deep brain stimulation. If you do, okay, sorry, just bear with me for a minute. We'll describe what it is, and then I'll talk a little bit about what we're doing as far as it's concerned. Deep brain stimulation is very useful therapeutically. For some people with epilepsy, it can help some people with Tourette's syndrome, but the main use is for Parkinson's disease. And what happens, and now there are a large number of people that have this treatment. You'll see there, there's a spindle with electrodes on the end of it, and it's called deep brain stimulation because that's exactly what it is. The electrodes are deep in the brain, either in the thalamus or typically the subthalamic nucleus, which is right in the center part of the brain. What the surgeon has to do is to drill down into the center part of the brain and then put this spindle with these electrodes down into the person's brain and then turn on the stimulating pulses. Now what you're going to see, just to see how effective this can be, is a person who has Parkinson's disease. You'll then see the assistants switch on the power packs, and you'll see how the person is with purely electrical stimulation of the brain, to see how deep brain stimulation works. Now the first thing to say here, some of you may, if you're into evolution, may have wondered why as humans we have all this space here. I mean, we've evolved, you can hear it echoing when you go like that. There's not really much here. We're full with organs and legs and bones and everywhere else, but here it's sort of empty. Well, what this is for putting pieces of technology. It's a wonderful prediction from evolution that we would need these spaces for technology, and the power packs for the Parkinson stimulator are positioned here. In this case, the person has right and left Parkinson, so they have power packs positioned on the right and left, and you'll see the assistants inductively switch on both power packs, and then you'll see, first of all, this is a genuine patient with Parkinson's disease. You'll see them first of all with Parkinson's disease, and then you'll see them in this case pure with just electronic stimulation of the brain to see how they are.
I'd like to show you in 2 minutes what was the status of Mr. Plessman when he was referred to us by his neurologist in Belgium. And you see him before surgery, without drug, unable to stand up by himself. He's helped by Patricia Limousin, who is a neurologist in our group, and he's not able to do anything of, as he will tell you, makes your life looking like normal. He's not able to walk. He has having dystonia, which are muscular contraction, deforming the different joints, and this is the best he could do without the drugs, with the help of people around him and mainly his wife and friends. He was referred because the drugs were not working anymore. He was not having any more improvement, and as he will tell you, he was just stuck to a wheelchair. This is after surgery. You see the tremor. We turn one of the two stimulators which were implanted with electrode into his subthalamic nucleus, which is a tiny part of the brain, and you see that in a few seconds the stimulation induces a stop of the tremor. This is still visible on the other side. We will turn on the stimulator on the right side, and you will see something even more spectacular than that. You will see that the patient feels again free, he moves, and he resets himself in his chair in the position where he feels the most comfortable. He will obey Dr. Pollack in doing some tests, even if he feels that those tests are a little bit useless as compared to the feeling he has. He can do that almost normally. On the right side, should I do it longer? Does he say? And he will show it on the other side. And then he will walk. He stood up alone. He's without any drug. You see him walking, turning. It was a few days before the Vienna meeting on movement disorder.
Now, I have to say the treatment works very well on numbers of people. Sometimes the patient may still need to take the dopamine, the typical chemical, but in some ways, for some patients, it can be like that the electronic stimulation works fine. One issue with it, however, is that it's actually pumping in quite a bit of electric current, and the power packs will only last so long. About 18 months to 2 years. There is a rechargeable version that you can recharge if it's still implanted, but patients simply do not want that at all because it involves lying down in a particular position for hours on end in order to recharge them in place. So the surgeon we work with in Oxford, the John Radcliffe Hospital, Tipu, as is, he doesn't actually implant the rechargeable version because patients just don't want to use it. They'd rather have, which is what has to happen, every 2 years they have to go back into hospital to have the surgeon open up, take out a power pack, throw it away and put another power pack in place. So it's a bit like changing the battery in a torch, and this has to happen every couple of years, which is quite traumatic for the patient. And anytime you have an operation, there's the possibility of infection getting in. So it's not particularly a good thing. So what we're doing with the surgeons is trying to make the power pack, the stimulator, effectively intelligent, so that it only stimulates when it needs to stimulate, not all the time. So what we're doing is using the electrodes, which are implanted in the brain, to also monitor the electrical activity in the brain, to feed that electrical activity into a computer, into an artificial intelligence system, which then learns to recognize from the electrical pulses deep in the brain when the tremors are actually occurring, but also to predict, which is a big advantage of artificial intelligence, to predict when the tremors are going to occur before they actually occur. And on many patients, we can get something like 20 seconds ahead accurately. So effectively, the artificial intelligence system is monitoring in real time what's going on in the patient's brain, and then essentially waving a flag and saying, hey, you're going to have tremors in 20 seconds time, with the view that this signal is then used to switch the stimulator on. And what we're doing now is trying to provide that feedback loop to actually assist patients. So the AI system is flagging, and now we're switching the stimulator on. So a different type of cyborg. Now for the last one, the last area to look at. Clearly it's the one you're all interested in, because I know you look as though most of you here are humans. Some are students, I'm not sure. And of course, as humans, we're really limited in what we can do, particularly mentally, how our brains operate in comparison with computers. I mean, you know, it's not particularly good, we can see that. I mean, if any of you want some hints on this, clearly memory, as I get older, I'm forgetting all sorts of things. Well, in comparison with computers, as a human, my memory is absolutely awful. Nothing like all the sort of memory capabilities of a computer. Senses, the third thing, we've seen something of ultrasonic senses before, which humans don't have. But in actual fact, we have 5 senses, which means we miss out on maybe about 95% of the signals around us. We miss out on so much information simply because we don't have the senses to take it on board. Ultrasonics, ultraviolet, X-ray signals, and so it goes on. Infrared, we just blasé, our brains just don't take the information in. So why not upgrade? Why not give yourself more senses so you can take a richer source of information in? Biggest of all, though, is communication. I mean, how humans communicate in comparison with technology, I mean, it's absolutely pathetic. We must all be so embarrassed about how we communicate compared to a computer. You know, how we can look computers in the face, I don't know. Because when you think about it, in our brains, we have highly complex electrochemical signals, ideas, thoughts, images, feelings, emotions, colours, all sorts of things going on in our brain. And if we want to communicate those to another human, what do? We translate those highly complex electrochemical signals into trivial, coded, mechanical pressure waves, serial signals. That's what I'm doing now. And this serial pressure wave has almost no connection with my initial thoughts, which were really rich in all sorts of ideas and colours. And those signals will travel very, very slowly, and someone else's ears will pick them up and convert the mechanical signals back into electrochemical signals, which almost bear no relation to the original thoughts and ideas. I mean, if you've been married for 40 or 50 years, you still have no idea. What are you trying to tell me, please? And teaching students, you know, you teach them, and it comes to the exam, and you think, oh, what a waste of time. Wouldn't it be much better if we could just send the signals directly from brain to brain? Zoom, there it is. We know you've got the message. Don't need to draw a thing on. Boom, there we go. I mean, or send signals from the computer down into the brain. Surely this would be much better. So in terms of communication alone, there's an enormous amount we could upgrade if we can just link together, if we can plug ourselves in. So a big advantage to consider moving ahead as cyborgs. Here's Campbell Ed. He lost his arm due to cancer, and he's been given this robot arm. But you see him operating a switch with his left hand, which in order to move the wrist and open the hand and so on, move the elbow, he's flicking a switch, there we go, and the elbow moves, which is a bit crazy, really. I mean, he's having to use one hand to operate the other hand. Wouldn't it be much better if he could just operate his robot hand from his brain directly and feel what the robot hand is feeling in his brain? I'll show you that again, there we go. Wouldn't it be better if brain signals go down from his brain onto his nervous system and onto the wires, and signals from the fingers on the wires go up to his brain? So he's got a bi-directional connection. All we need for that is a bi-directional interface. An interface from the nervous system to the wires. That's it, that works in 2 directions. Simple as that. Let's assume for a moment we've got it, a bi-directional interface. Great. If somebody's lost the use of their hand or arm, or they've lost the use of the legs, then as long as the technology is there mechanically, we can give them an artificial leg or hand or arm. And they can control it from their brain and feel what it feels in their brain. But that's still thinking therapeutically. That's thinking in the box. Because here, what we're talking about, if we have that bidirectional interface, we have a link from the brain onto wires directly. And those wires, we don't have to connect them up to a leg or arm. We can plug those wires into a computer. We can plug it into a network. We can send those brain signals across the internet, if you like. So if you want to think of it that way, you can have body parts wherever the internet takes you. You know, you don't have to have them now attached to your body where you are sitting. Well, your body is wherever the network is. So what we're looking at here is, if we have this technology, a bidirectional interface from the nervous system to wires, then your brain and your body do not have to be in the same place. It's as simple as that. Brain can be in one place, your body can be wherever you want it to be. So what have I done in that area? Here's me lying on the operating theatre. I have to say this wasn't an operation I had to have for medical purposes. This was something for scientific research. It was a 2-hour operation to have this thing implanted. This is called the Utah array. It's also called the brain gate, and I was the first human to have this implanted. It's being used a bit more now, particularly in the US. Essentially, it consists of 100 spikes. At the end of each of those spikes, each of the spikes are 1.5 millimeters long. So 1.5 millimeters, this was fired into the nervous system of my left arm. Now the nerves, this is the median nerves, the main bunch of nerve fibers, like going from the brain down to the hand. All of the nerves in total are about 4 millimeters in diameter. So this was fired in, bang, 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 about halfway. The electrodes, which make the connection, which you can send signals in or out, are about 2 micrometers across. So on the tips of the spikes are the electrodes, which are about 2 micrometers across. Now that is the sort of size for neurons or nerve fibers. Typical neuron, 2 micrometers, up to maybe about 20 micrometers. The same for nerve fibers, which means that the sort of resolution that you can get with this, either through stimulating or measurement, it is probably you're dealing with just a few, you know, maybe 2 or 3 neurons, nerve fibers, either measuring or actually stimulating them. You could actually be stimulating individual nerve fibers. So you're getting very, very high resolution compared to putting electrodes on the outside of your head, where you're getting much, much weaker signals that are affected by noise big time, and also you're dealing with millions of neurons. You're picking up average signals from millions. Here, with this, you're dealing potentially with just 2 or 3 neurons. So you're getting very, very high resolution. Sorry if you did eat quite a bit beforehand. This is my left arm during the operation, and what the surgeons had to do was to make 2 incisions, and then they pushed that tube down between the incisions. That array of 100 electrodes, they pushed down the tube, they removed the tube, hammered the electrodes into my nervous system, stitched me up. I had then, for 3 months of the experiment, I had the electrodes in my nervous system, wires running up my arm, and coming out, the little green thing that the surgeon's holding there is a connector pad. Literally, the gold terminals were connected into the electrodes in my nervous system. So this was like pulling my nervous system electrically out of my body via those terminals, which meant that I had to, if I was having a shower, I had to keep my arm out of the shower, otherwise could easily have short-circuited my nervous system. So, we were able to plug in either directly into the computer or by radio, plug my nervous system into the computer. So what happened essentially, if I opened and closed my hand, we could pick up quite clearly the neural signals that did that. It's not difficult, in fact, and send those signals via the computer to pieces of technology. So I could operate via my neural signals different pieces of technology. but also over a 6-week period we put current signals down into my nervous system, so we push current into my nervous system that my brain learnt to recognize the pulses over a 6-week period. So then we could stimulate and try different sensory input and so on. So I'm going to show you, I've got a clip from Discovery TV to show you some of the things that I could do with this implant.
One man in tune with technology is the world's first cyborg. Part man, part machine. Kevin Warwick, cybernetics professor at Reading University, England, took a leap into the future as long ago as 2002. For 3 months, a silicon chip was implanted into the nerves in his arm.
At that time, no human had had an implant of this type before.
It was a procedure that until then had only been tested on chickens.
Would the body reject it? Would it affect the way I moved or my sensory capabilities? I could have lost the use of my hand. Could it affect my brain? Ultimately, could have sent me crazy.
Kevin was plugged into a computer which monitored the nerve signals from his brain to his arm, receiving and transmitting them as radio waves. With the signals from his brain, Kevin could not only turn on lights, he could control a wheelchair. And from 5,000 kilometers away via the internet, he succeeded in getting a robot hand to mimic his own hand movements. His most impressive experiment involved his wife, Irena, also having a chip implanted in her arm.
The communication experiment between myself and Irena was vitally important to me. This was the highlight of the whole experiment.
Kevin wanted to discover if it was possible for his brain to receive and feel signals from Irena's brain.
When Irena first moved her hand, it actually felt like a charge running up my index finger. It was a phenomenal feeling. Literally, every time she moved, my brain received a signal. There we were communicating for the first time in the world, nervous system to nervous system.
It was the first time two people had electronically communicated by thought alone.
In the short term, we're going to see implants used to help people who are paralysed switch on lights, operate the TV, just by thinking about it.
In 30 years, he believes we'll all have chips in our brains.
But ultimately, having extra memory, having downloads from the computer, uploading from the brain. Earth is going to be controlled by cyborgs. Humans are going to be something of a subspecies.
We'll be half man, half machine, with super memory, super senses and superpowers.
I think quite clearly that's where we're going. Superhuman. Well, obvious, isn't it? So I think a little bit of Nietzschean philosophy for you to finish that. I've got now just a few holiday snaps to conclude with, just based on what the experiments were about. The ultrasonics we've heard of before. Well, in this case, for the experiment, the implant was in my nervous system. The baseball cap has ultrasonic sensors on it. The output from the ultrasonic sensors this time was fed into my nervous system effectively. So my brain was receiving pulses of current that increased in frequency the closer an object came, and decreased in frequency as an object went further away. So it was experimenting with an ultrasonic sense, and could the brain extend to having new sensory input, which it did do straight away. So we can have new senses, at least ultrasonic, which is a fairly straightforward one. This is my wife Irena, and she's from Prague, so not too far away, and she's got some jewellery that a student at the Royal College of Art in London put together. The jewellery changes colour from red to blue. Now, there's different ways it could work, but if you can imagine the scene, because the jewellery was linked via my implant to my nervous system. So dependent on the signals on my nervous system, that indicated what colour the jewellery was for my wife. So imagine the scene. I'm calm and relaxed, and my wife's jewellery is blue. I get excited and my wife's jewellery starts flashing red. So she doesn't work in the university at all. There she is in her office and the jewellery is blue. Fine, he's not doing anything he shouldn't. And then the jewellery starts flashing red. What is he doing? And more importantly, who is he doing it with? It's perhaps not such a good idea. This was taken at Columbia University, New York, and what we did there with the guys in the real-time computing lab was to plug my nervous system into the internet in real time. So it actually had an IP address. So if somebody had known what the address was, they would have been able to hack in and all that sort of thing. The main security was that we didn't tell people what we were doing until after we'd done it. But we linked up. So I was in New York with my nervous system, obviously, and we linked up to the robot hand, which you saw earlier on Campbell Aird, but the robot hand was in Reading, in England, but it was linked to me electrically via the internet. So I moved my hand, closed my hand in New York, my neural signals went across the internet to close the robot hand in Reading. When the robot hand gripped an object, signals were sent from the fingertips of the robot hand back across the internet to stimulate my nervous system in New York. And again, with this increased number of pulses. So the more the hand gripped, the more pressure, the more pulses my brain was receiving. So I could feel how much force the robot hand was applying on another continent. And clearly, for somebody who's lost their arm, they could use the same technology for a replacement arm, which again, now there are 2 or 3 groups around the world that are looking to do that. But you know, it also means the arm doesn't have to be attached to the body. The arm, whatever technology you want, can be wherever you want it to be. The other thing we did, which I think something similar has just eventually in America been done with rats. It only took them 10 years to do it with rats, but we did it with humans in Europe. And what we did with my wife, she had electrodes pushed into her nervous system, and electrically we linked our nervous systems together. So when she closed her hand, my brain received a pulse. So we did a, if you like, telegraphic communication, very, very simple form of communication. Tick, 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 tick. So I could take a number of pulses. And back the other way. If I closed my hand, then that stimulated her nervous system. So we did telegraphic communication, nervous system to nervous system. And clearly where this is going is direct brain-to-brain communication between humans, and that's the experiment I want to do. I have to say, my wife Irena, for some reason, I don't know why, feels that brain implants are perhaps a little bit dangerous to do this brain-to-brain communication. I'm on for it though, so if there is a volunteer in the audience, please let me know, because that's the next step in these experiments. Thank you very much for listening. Hope you've enjoyed it, and enjoy the rest of the conference.
Do we have any questions?
Hi, that was a really great presentation, and it made me think about hundreds of questions, so it felt really inspiring, but I think the most important for me would be, how do you make brains want something? So you put them on electrodes, you get the robot to run as the brain stimulates it, and then how do you make robot want to turn right?
Right. Again, like you said, there's hundreds of questions. I've got hundreds of answers to go on that. Literally what we do with that is very, very simple. After the 10 days, we will stimulate on different electrodes, and we will see where we get a response within a short period of time, talking in terms of milliseconds. So let's say if I stimulate on electrode 67, and I get a response a fraction of a second later on electrode 21, and that happens one time in 5, let's say. So that it looks as though there is some sort of passageway in, the nerve fibers in the brain have connected up. So that's what we use, and that's what you saw in that first, with the robot starting off. You saw it getting it right, maybe, one time out of 5, or maybe a little bit better than that, but it was that sort of thing. And so we're actually choosing some sort of pathway and creating the feedback loop. But the point is that every time it stimulates and fires that pathway, the pathway strengthens. This is habitual learning. Every time it does something, whether it's good or bad or whatever, it does it, and so on and so on. So and then you saw after 2 months, the pathways have strengthened so much that that's all it does. It never does anything else, which is a thing with habits that now. So that's that point. With rats and monkeys and I guess humans, it is well known where the pleasure zones are, where you can stimulate in the brain. So that this is answering your question from a different point. So in tests many years ago, there's a guy called Olds did some tests, firstly on rats, where he gave them a choice. Either they could press a button and be given some food, a liquid treat and food and things like that, or they could press another button and they had their pleasure zones stimulated. So it was their choice, and by a feedback loop. And what he found was, amazing though it might seem, is that what the rats did was to press the button to get the pleasure, and they pressed the button to get the pleasure, and in the end starved themselves. They just never ate. They would go for the pleasure zone. He then repeated the experiments with chimpanzees and found exactly the same results. And to be honest, we find in humans, you think, oh, humans are much cleverer than, well, with, in a practical scenario with drugs, and you do find some people, I know there was a wonderful footballer called George Best, and he kept drinking too much alcohol, and they said, if you keep drinking, you're going to die. He kept drinking and he died. Which is the same sort of thing, is stimulating the pleasure zones, and you get that sort of activity with humans. So if we know in our culture, if there is a pleasure zone, where the pleasure zone is, then we could start doing the same sort of techniques to get it to, for positive feedback, rewards if it does something good. But at the moment, we don't know. Does it have a pleasure zone, or how do we stimulate? We don't know that. We can apply sort of reinforcement learning, positive and negative feedback, chemically. So we can look at the brain. If we see pathways that are used in it doing something that we want it to do, we can apply chemicals to enhance growth in that region. Or we can apply chemicals to restrict growth, or to cause part of the brain to die off. So we can do that in a sort of, we're guessing where we think the pathways are, which gives something of reinforcement learning, but the ultimate would be the hitting the pleasure zones if we knew where they are. I'm sure someone else will discover where the pleasure zones are, and they'll win the Nobel Prize for it or something like that, and then we'll move forward. But at the moment we don't know. And again, because we're sort of actually laying these brain cells down in a fairly random way, it might be that the pleasure zones, if there are any, are in a different place in each culture. So it presents, how do we find out where they are? We don't know really. So it's quite a problem. But it's exciting from a research point of view.
And the next question?
Do you think that it will be possible to achieve some sort of immortality by moving a brain to cyborg, or but just the content of the brain of human?
Well, I hope so. I don't know the answer. When you say some sort of immortality, I think people are looking to it. We are anyway, on average living a bit longer, bit by bit by bit. And there's all sorts of ways we could enhance that a lot more. Whether we actually get immortality or not, I would think, number one way that would help things very, very quickly is if we get rid of our bodies. So, our physical bodies, what do we got them for? Our brains are the critical thing. So, as long as we can keep our brains alive without our bodies, that would be, because there's a lot of problems we have with a lot of cancers, a lot of the body wears out, your heart stops, that if you could get rid of all that, that would very quickly move things forward. And hence I feel there's a lot of money we're spending on research into cancer and heart disease. And I think, well, let's stop that. That's silly. That's just a short-term fix. Let's spend that money on developing research to keep brains alive outside a body. That would be a much better, to answer the question. I can't imagine people will quickly do that, but to get there it would be nice if they did. Second point then all the problem is just the brain. So it's a simple problem. Either downloading the brain, Moravec style, into a computer. Will that be possible? I mean, if we could, or can work out how to do it, then fine, we've solved. First of all, it's only the brain, and now we've got the brain in a computer. That's fine. As long as nobody throws you on a heap or throws you out the window, you're all right. You can live forever. But in terms of, as long as part of your brain is a biological brain, then the answer is simply if we can rejuvenate it, if we can apply new neurons or apply stem cells so that you retain the memories, you keep going, then yeah, I mean, so I would see, yes, it would look to be a possibility, and I've removed a fair chunk of the problem, which is the body. So if we can do that, then I think if we keep our bodies, then we've got all the problems of keeping the body alive. That, the brain, and I mean, it's a great shame. People that have the brain is still fully functioning, and something goes wrong with the body, which, I mean, it's only there to carry your brain around, let's face it, which is a great shame for people to die for something that is not a problem with their brain. I don't know if that answered. I tried to give you a technical, practical, realistic, I would like to think, answer.
Who has no questions?
I mean, I just, while she's going around there, Aubrey de Grey, of course, looks at it more statistically and says, I think every 10 years our life expectancy increases effectively another 2 years, if you like. So if we can get that statistic, so every 10 years our life expectancy increases 11 years, then it's purely a statistical thing. If we can achieve that, then of course we will live anyway forever. So just looking, instead of it increasing 2 years every 10, we can push that up to 11, but that's another.
Have you ever tried to use the implants together with the virtual reality? So that person can feel the virtual rock or something like that when he picks it up?
I have to say I haven't, no. It is something, at Reading we've got a virtual reality cave, so it was something potentially could have done with that experiment. Not virtual reality, well, I say that, what Ian, who it's difficult for me to tell you because he's got a commercial sponsor which would give the game away of what he's doing, but he, with his magnets, effectively he is doing that. It's not so much a virtual reality, but it's a simulation, and he's getting stimulation through, so he is part of the simulation, if you like. He's receiving, but I can't really tell you the nature of the simulation, but there is a simulation. It's effectively like his body is part of the simulation, so he's getting feedback through that. So in the magnet implanted case, that is what he's trying there. But I have to say, in a more general sense, it's something that I could have done, perhaps, but I didn't do. It's a good idea, yeah. I mean, are you thinking Matrix, or?
All right, I've got a question. Hello. So I'm interested in habitual learning, in the one you've mentioned before. And my question is, from the neurological point of view, what are the most efficient ways of weakening the link between neurons, thus to eventually quit some habits, and how far did science go as for now in that area?
Yeah. More. Each question is very, very good question. I can probably only give you a partial answer based on my own experience. First of all, you can never be completely sure which pathways are involved, and sometimes because of the way the neurons act, it may be it takes, uses these neurons one time and maybe it uses these neurons the next time. It's a big advantage of how the brain and the nervous system works, that it adapts a little bit and changes. So you've got to try and guess a little bit. Let us assume for the moment that we knew this pathway is being used. Then we can apply chemicals to, quick kill off. We can do, boom, stop it. So if we do know this region of the brain is active every time it does this, we can just go in and apply chemicals to kill the brain off. Yeah, or we could start cutting. We could break the links. To actually do that on let's take it to a human brain, well, that's where I do have a practical experience, because when I was about 9, my father had the opposite of claustrophobia, agoraphobia, when essentially he could not go. This is my first experience, I guess, with neurological problems. He could not go outside. In the end, he could not go outside the house, and then he was stuck to a room, so he couldn't work or anything like that. And one of the vivid memories I have is of him they tried different drugs, and he was just getting worse and worse and worse. So okay, it's a phobia, but in this case he really had it extreme form. And I can remember them dragging him out of the house to go to the hospital with him, screaming, and he was red and sweating. It was horrific for him. And they operated on him and gave him a leucotomy. They cut out part of his brain. They broke. Now, in talking to surgeons later on in my life, they said, wow, they don't do this anymore. For him, it worked. For him, it worked. When he came back home, he was in hospital for several months. When he came back home, he had a bad temper for some reason, but he was great. He would talk to anybody. He would go out and, he would talk to people in the street. He was completely the opposite, purely through this neurosurgical operation. So not only did it break the habit, but it completely changed his character. After a year or so, his bad temper that he got went away, and he was really nice guy. I mean, he really was not. You should have met him. He really was a nice guy. But he got rid of his agoraphobia simply by snipping out some. I mean, he always thought that the surgeon, quite rightly, was a miracle worker, as it were. And when you'd seen him before and after, it was very much like that Parkinson disease guy over a longer period of time. There he was, confined to a room, and here he was, the nicest guy, would go anywhere and talk to anybody. So there's a practical experience that it is quite possible to do that, but I think it is a very, very risky business, and I think it's only extreme cases that they would ever operate like that. Whether they do now, I don't know. And therefore it would be, if you're just trying to quit smoking, it would be quite a risk to take. But so it might get rid of smoking, but there we go.
Any more questions?
What do you think about nanorobots? It's still biotechnology. So what do you think about nanorobots? It's our body, in human body.
Yeah, I mean, first of all, when we say nano robots, what we mean is very small robots. Whether they're actually nanoscale, with a lot of things, because they're talking about micro air vehicles, which are not micro at all, and now they're talking about nano air vehicles, which are actually about 10 centimeters across or something. You know, it's not nano, it's just that it's quite small. But I think in this case, obviously, they have to be very, very small. I think it's an exciting future possibility. I mean, as far as I am aware, what we have at the moment are small imprinted, what look like gears and so on, but they're not. It's not the sort of thing you can inject in your bloodstream and it goes down and does an operation in you. But I think if we're looking to the future, how do you power them is an issue. Do they have the power themselves, or can they pick up power inductively? Sorry, I'm looking practically at the thing. If they do have an antenna to pick up power, like the first implant that I had, then the antenna tends to be quite big if it needs power to move around and so on. And then, you know, how is it communicating? Or is it completely, if it's self-contained, it will need some processing capabilities. So there are lots of practical issues, but that's just practical issues that need to be sorted out. So overall, I feel it is a very exciting future, but it needs quite a bit of research. Now, the big thing, I think, from a surgical point of view, as much as you can minimize how much you cut open the body is better. And that's where keyhole surgery and fiber optic technology really moved surgery forward. That to carry out a lot of operations, you didn't need to actually really open up the body, and that really reduced the number of fatalities, the number of people that suffered other problems due to infections getting in when it came to surgery. So nano robots, where you don't actually need to cut anybody open, have an enormous future if they can be achieved. But at the present time, I think I believe there are quite a few technological problems that do need to be sorted out to make them become a reality. It may well be the first step is if there's one particular surgery that they could deal with, a simple task, as has been the case with robotic surgery. They dealt with some specific tasks that were fairly repetitive, and they're very useful for that. So in this case, if there's a specific task, it can be purpose designed, it can be maybe injected into a particular place, doesn't have to move very much, and it just goes and does the job. So a particular thing could push things forward. But power, communication, those are the sort of problems, I think, which are perhaps holding it back at the moment. Don't know if is that answered? But I do see it as a very, very exciting, 10 years' time, I think we're going to see maybe the first experiments in that area, that sort of thing. Certainly the materials, I think, are there. The materials are there to do it. I don't see that as a problem.